Okay, so good morning, and this will be the last formal lecture for this course. And the main agenda item today is to reformulate mechanics in special theory of relativity. And so before that, I want to do something interesting, some fun stuff. Okay, so the fun stuff is, two predictions from SR, in particular involving Lorentz-Booth. Okay, and those two things are uh, one is called time dilation, and the other is called Lorentz contraction. Okay, so we'll do this first. And so what we will do, we'll begin with a setup where, for simplicity, we will consider Lorentz-Booth in the x direction. And I will kind of ignore the other two guys. So let's just write. And we will study displacements in space-time. Okay. So again, there are two frames, A and B, and we use x and t for frame A and x prime t prime for frame B. Okay, so let's just write this, C delta t.
Sir, is it really Lorentz contraction and not length contraction? I mean the term, the name.
I think it's called Lorentz contractions. I don't know. I mean, that's what I usually call it.
Oh, okay, sir.
It's a contraction of length. You're right. I mean, okay. So
yes, sir. Okay.
Okay. Yeah, what you're saying is correct. But I'm not very good with names, so I could be wrong. But we can check that later. Or somebody can check online. Okay, so I'm using a plus sign here. Huh?
Lorentz contraction is also correct.
Okay, thank you. Okay, so this is the formula which we have worked out already. Okay, so what I mean by delta x and delta t is that there are two events A and B. Okay, and let's say this is located at x1 t x vector t1 x1, and this is at t2 x2. Okay, so delta t is say t2 minus t1, and delta x vector is okay. So this is just that we are putting things. So there are two events we need to get a displacement, right? We one won't do, and of course here there is delta y prime is y and delta z prime is z. So but we won't worry about that. Okay. So first one we will do is something called time dilation. Okay, so this is so we will consider time interval delta t in frame A, of course, with delta x being 0. Okay, and then we can ask, okay, so the time interval delta t in this thing. So we can just go back there and look at delta t prime. C delta t prime would be cos phi C delta t, and recall gamma factor, which was 1 by square root of 1 minus beta square or u square by c square, which is always greater than or equal to 1, is equal to, in this language, cosine hyperbolic of phi. Okay, so if we just put this together, we get delta prime is equal to gamma delta t. Okay, so what this says is that if you have a pure an interval, a time interval in frame A, the same time interval will be expanded by a factor, so it dilates. Okay, so gamma is a dilation factor. Okay, what is very interesting is that similarly, if you consider in frame B, if you consider time interval delta t prime, okay, you again that will correspond to this thing. There will be time dilation of that also in happening in frame A. Okay, so it's symmetric in a weird way. Okay, so this is the dilation factor, and the key point is it's always greater than or equal to 1. Okay, so let's try to make sense of this. So consider, so let's use this. Consider a sample, a radioactive sample. Okay, in frame A with N0 particles, or radioactive particles at t equal to 0. So it's at some point. So it's like we have a container and we have a way of measuring how many particles of that radioactive sample are there. And so from radioactivity, we know the following, that dN by dt, it will keep where n of t is this thing, will be minus lambda n of t. Okay, so lambda is dependent. So this is related to the so-called time constant of this thing, and so we will see that n of t, n0, I called it n subscript 0, right? Let's call it, use the same notation. Okay, so what this says is that n of t by n naught is e power minus lambda t. Okay, and lambda is a property of the sample. Okay, so this is a system we're going to study. Okay, in frame A, okay, the sample, the radioactive sample is at rest. Okay, so if you wait, okay, so for instance, so let's do something. So let me let tau be 1 by lambda. Okay, then at time tau, how many we would observe? That what is n of tau? That's all I'm asking. That n of tau, what will it be equal to? Somebody.
It's N naught by E.
Yeah, it will reduce by a factor of E. Okay. So now the same process. So frame B, a person in frame B okay, will assign a time. What will be the time B? Okay, assign a time tau prime to when, say, she sees N0 by E particles in the radioactive bar in the sample. So how is tau prime related to tau? Right, because this was an interval, so 0 to tau, it went down. So this interval will get expanded to tau prime. Okay, so observer B will say that the lifetime of the moving sample is larger by gamma. Do you agree with this point? Okay, so time is getting dilated, so lifetimes get dilated also. Okay, so this is an example of an application of this simple formula here. Is this point clear? And the point here is that this lambda, which is usually assigned to a sample, is done in a lab where the sample is at rest. Okay, so what we are doing now is we are asking somebody can, track, somebody in a moving frame can track these things and ask what's going on. Okay, so this is the prediction. Okay, is this clear? So what one says here is that moving clocks run slow. Okay, I'm not great with all these mantras or whatever. Run slow. Okay, so that actually takes longer. Okay. Anyway, so what I want to say here is that this was actually this kind of experiment is carried out by Frisch and Smith in the 60s, I guess. In an experiment involving subatomic particles called muons. They were called mu mesons in those days. Okay, and but the source of the muons is from cosmos. Okay, it's the cosmic flux. There's always in particular, it is known that the flux, the number of particles per unit time, that the flux of muons is constant. Okay, this is an experimental fact, reasonably this thing. Okay, so the experiment done was like this. So they went to a mountain top. This is my version of the mountain top. It is H. Okay, so they measured flux here. Okay, and then they measure flux here. Okay, and muons are known particles. We know their lifetimes. Okay, estimated. Okay, so what they did was, but they did very, very clever. Now you might say, when cosmic muons are coming, how can we fix their velocities, right? How can, so here, so this is the issue. And so what I want to say is that I'll share this article. They cleverly focused on particles, on muons, with specific, with velocities, okay, in a tight range. And these were, with ultra-relativistic velocities, it means close to this thing, ultra-relativistic velocities. So gamma, gamma is, I think, 10 or something like that at least. Okay, so it was some reasonable factor. And to first order, you can say that they're almost moving at the speed of light. So the time it takes to come from here to here, delta t will be approximately c by h by c. Okay, so they can use the same similar formula and estimate the lifetime. And because they know the gamma factor, they can check. Okay, so they should see, so what they should see is n of t. Okay, now n here is, we have to do, is flux, doesn't matter, it's like, for the formula purposes, they should see n of t equal to the flux. This is at the top, mountain top, and this is at this thing. And this t here is this t, delta t or whatever. Okay, lambda is known from lab measurements. So muons at rest in some sense. We know lambda. H is the thing of the mountain. We know C. So then they are fixing some, so they can estimate by, they are measuring this and they know this. These two are two measurements, and so they get gamma. But they also have a way of finding out what the velocities are. They can compute. So they have two different measurements. Okay. Is this clear? Is the experiment clear? Okay. So they actually did this thing, and so there is a beautiful, I will add this thing, so I will provide there is a very nice article in the American Journal of Physics where this experiment is explained in detail. Okay, and they made a movie. Okay, so both will be shared. I'll share this. This will be shared on Moodle. Okay, I'll put it in the category of must watch. Okay, so there are things like how did they select the muons with a range of speeds? How did they account for the thick layer of air which is there? How did they detect muons? Okay, and so this is something which I would strongly recommend that you see, because this is really what for me, more than the theoretical part, is the experimental aspects of that experiment is just spectacularly good. And So that is as impressive as, the prediction of time dilation. Okay. So, of course, there is, popular science or popular fiction, science fiction, there is something called a twin paradox. Okay. And which is Crackpot's favorite. One of Crackpot's favorite things. Okay. So there's something called the twin paradox. There isn't one. First point is there is no paradox. Okay. So what is a twin paradox? Yeah. Let me explain what a twin paradox is first. Okay. So the idea here is follows, that there are a pair of twins. They are of course the same age, right? So then you separate them, and one travels at for some time at the speed of light and then comes back. Okay. So now the question is, they should differ in age due to time dilation. So who will be younger? Who will be this? This is the thing. And now you would say from relativity that each should see the other as younger, right? This is what I explained to you, that if somebody was rest in somebody's frame, in some frame A, that person's that time duration will get dilated in frame B, but the converse is also true. If there's somebody in rest in frame B, their thing will get dilated. So the question is, there is a symmetry in that thing, but in this problem, there is an asymmetry in the problem. Okay, and the asymmetry is that to go and come back, there is only one person who is going to, it's true, has to feel accelerations. That is not inertial things. So somebody has to accelerate first to go to some high speed, and then go this way, and then they have to decelerate to turn back and come back, say, at the same speed, and then again further decelerate to stop. So there will be one person who is going to feel all the forces. Okay, so there is not, basically the paradox is not there because there is no symmetry in the problem. The symmetry which I pointed out is not there. Is this clear? Okay, and so there is no paradox, but there is a nicer experiment people did. So which is the analog of the twin paradox, but it's more complex. I'll explain why. So we have atomic clocks which work to very, very high precision, right? You know that. So we had two atomic clocks which were synchronized, and one of them was taken on a supersonic jet, which is pretty fast, and that circled around the Earth a few times and came back. Okay, and then so delta t. When they come back, there is a difference between these two clocks. And of course, the reason this is complicated is that Earth is not an inertial frame, as we know. So in addition to SR, there are general relativity effects as well. But there's a beautiful way of, Earth is not considered strong gravity. Strong gravity is, just outside a neutron star or a black hole or something like that, Neutron star is probably correct. And so that's good enough. So those will have strong gravitational effects. But here it's a weak effect. But there's a very nice method of computing this in a book on general relativity by Hartle, but it's beyond our syllabus. But then you can do the computation. It has both special relativity effect, time dilation, and it turns out that the GR effect has the opposite sign. So delta t, it makes it smaller, but you can compute both of them and then put them together. And because both are reasonably small, you can add them. You don't have to worry about, cross terms and things like that. They're too small. So you can actually do this, and you find exact agreement with the special theory of relativity and general theory of relativity. So it's checking two different effects. So I just want to tell you that there is no twin paradox, etc. But okay, and so that is the. So don't, if crackpots come and try to ask you, oh, you are a physics graduate, maybe you can tell me. I would suggest that you don't even waste your time. Okay.
Sir, what if we broke down the moving person into many inertial frames of different velocities?
And now you're asking, you want to do some violence to that person, right? That means you want to pull them apart, etc. Sorry, that sounds very gory. Let's not discuss it. I would rather have multiple objects. So, for instance, a rigid body or something like that. Okay, you can. If they are now, it's no longer rigid, right? If you start saying they are moving, that means points are moving with respect to each other. within that thing. So it's no longer a rigid body.
I didn't mean that actually. What I meant was like at t equal to 0 to 1 second, it is at a certain velocity, and it is initial. From 1 to 2 seconds.
Oh yeah, yeah. What you're saying is that there is acceleration involved. It will only complicate the story, but yeah. Okay. So to simplify things, so the idea is that there is a short period of acceleration where that person will go and reach some uniform velocity, and then you go constant till there. Then again, there's a short period of deceleration, turn around, come back, say to the same velocity, and then come back, and again another short period of deceleration, and then back. Okay, so that's the simplest situation. You could have completely non-uniform things. Okay, so but for instance, the computation I just mentioned that takes care of, it can even handle non-uniform things. Okay.
Okay.
So now let's do the second one. Lorentz contraction. So in special relativity, it's very important to ask the right questions. So for in Lorentz contraction, if you're careless, you will, what you will do is you will end up getting Lorentz expansion, which is crazy. That means you're asking the wrong question. So we have to be a little bit pedantic and careful. So we'll do that. Okay. So there's a ruler of length L at rest in frame A. Okay. So let's say we place it in the x direction itself, so that if it were not placed in the x, if it were in the y direction, there is no contraction. Okay, because that's the direction which is perpendicular to this thing. So this is x direction, say this is y. Okay, so what does observer A do? They will. So the idea here is that there are two events, but you measure them at the same time. So this will be so A will be. We'll ignore all the other coordinates. It will be at say the same sometime t0, 0, and this will be same time we will measure it. Right? That's what we do. Whenever we measure length of something, we don't measure it at two different times. Okay, this is roughly okay. Now, what does observer B do? Observer B also. Okay, so in this setup, delta t was 0 because we are doing this thing. But here, this person will require delta t prime to be 0. Okay, but now because the thing is moving, delta t prime equal to 0 implies that c delta t equal to tan hyperbolic phi times delta x. Okay. Further, so we want to ask what is delta x prime, which is what, but c delta x prime will be equal to so c delta x prime will be equal to what is it? Why is it c delta x? No, it's just delta x prime will be equal to sine hyperbolic phi c delta t plus cos okay. This is fine. Okay.
Yes, sir.
So delta t, knowing some sign issues, so that's okay. That's fine. So delta t prime should be 0. So and we can substitute for delta t in this thing, so it will be
so there is a minus sign that comes
Yeah, that's what I'm messing up my minus. Yeah, there is a minus sign that I messed up. Yeah, that's what I was looking for while I was correcting my thing. Yeah, thanks. That's a minus sign. Yeah, because it's delta t prime equal to 0, so that this is minus. Thank you. So then I substitute for c delta t in terms of this. So it becomes sin h phi minus tan h phi plus cos h phi into delta x. Okay, and we'll take delta x to be the length. Okay, this is what we want. But now we have to simplify this. So this just becomes equal to, I can pull out a 1 by cos h phi times okay. So what is happening is now gamma is, remember, is greater than or equal to 1. So you can see that L prime is less than or equal to L. Okay, so this is what is called Lorentz contraction. Okay, so it just says, I mean, the way I remember things about time dilation as well as Lorentz contraction is the following. I just remember that the time dilation is that the time is the smallest in the frame where the time thing is at rest, and similarly the length is the largest when something is at rest. Okay, in the frame where that object is at rest. So this is just something which I just want to point out. That's all. Okay, so these are the two nice things, and now I'll pause here for questions. If not, we will move on to the topic of the day, which is mechanics in SR. Okay. So the key ideas are we need to define, the idea of define velocities. So really, what we want to do is define 4 vectors, okay, associated with velocity, acceleration, force, etc. Okay. Okay. So once we do that thing, we can write. Once this we done, once we do this, we can write Newton's second law. F equal to ma in covariant form. Okay, so the idea here is that Einstein did not prove Newton wrong. He just extended the regime of validity. So there must be the reverse should hold. So Einstein is a guy who has to say that whatever equations he is writing better reduce to Newton's equations in some limit. Just as we saw that Lorentz boosts reduced to Galilean boosts. We know that. So whatever laws we write for particle motion in special relativity, they should be natural generalizations of Newton's second law. Is this point clear?
Sir, your screen is not visible.
It went off?
Yes, sir.
It's frozen.
It's frozen.
Okay, let me just come and see what's going on. Sometimes it happens. My presentation itself is gone. No, it is there. Stop presenting.
So it is stuck at L prime is equal to L by gamma.
Okay, I'll share again. Sorry, thanks for telling me. Now?
Yes, sir. Now it's visible.
Now can you still see it?
Yes, sir.
Yes, sir.
Yes.
It's moving? Okay.
Yes.
So this is all I wrote. I said we need to define 4 vectors, and then I want to say this. Okay, is this clear? So this is our idea. So let us just, so what we want to do is, we want to study the motion of a particle of mass m. Okay. Okay. Now the key point is, so if you wait, so let's say that initially it was, so we should study displacements, right? That's what we are told. So, but we know that, so let's say that delta x mu is the displacement of the particle in space-time. This we know is a 4 vector. Okay, that's it. So from this we can construct a quantity which we will call delta s square, which is just a norm of this, which we'll write as c square delta t square minus delta x dot delta. Okay, so this is just an infinitesimal change in the position of the particle in space-time. Okay, and we know that since this we also know should be greater than 0. Okay, because it's for instance a particle could be not moving, right? So in such a situation we expect that just delta t is non-zero and delta x is 0, so it will just evolve. In space-time it will be moving in a straight line which is horizontal. Okay, and of course first thing is that just some remarks now. Of course, there exists an instantaneous inertial frame where the particle is at rest. Right? Remember, I'm saying that the particle could be accelerating, but at any instant it has a given velocity. So for that instant, I can find a frame. Next instant, I have to find a different frame. So that's all I'm saying. So in that frame, delta x will be 0. And that's again, that's one way of saying that delta square is greater than 0. Okay. But in an arbitrary inertial frame, okay, and so what we will do is, instead of calling this delta s, I'll call it delta tau. Okay, so let's okay, so let delta tau be delta s. Okay, so we'll call this tau, we will call, has a name called proper time. Proper time is not one word, sorry. Okay. So what we will see is that delta tau square is equal to c square delta t square minus delta x dot delta. So we can pull out, this is equal to one minus, say, the velocity. So if I pull out delta x by delta t, okay, we'll just call this v. That's just the instantaneous velocity of the particle in that frame. Okay, so this is equal to 1 minus r. Okay, is this clear? So what we see from here is that delta tau is equal to, so I can cancel c's, and you see this is 1 minus v square by c square. It's just like a inverse of a gamma factor. So this is equal to delta t, but the gamma factor associated with v. Okay, so let me explain what one means. So v would be the speed of the inertial frame where it's at rest, instantaneous. So this is what we get. So we get a nice formula which says that d tau by dt is equal to 1 by gamma of v. Okay, and remember, I'm not saying v is a constant or anything. Okay, so what we do now, this is just this. So now I will define for you a 4 vector u mu as follows. So remember d tau is a Lorentz invariant. So this is just defined to be Tx mu by C d tau. Okay, tau is the proper time. Okay, so this is a this is a 4 vector is obvious. Okay, but now we can ask. So this we'll call it a velocity 4 vector. In a moment you'll see why. Okay, and so we can go ahead and compute its components. So you look at u0. What will u0 be? Dx0, which is c dt, is dt by d tau. D tau, sorry, dt by d tau, not d tau. Okay, and we just saw that d tau by dt is this thing. So this is equal to gamma times v. Okay, and what is ui? Okay, so which we can write as dt by d tau into 1 by c times this thing times dxi by dt. What should we call this? Vi, right? So we got the components of this 4 vector. So u mu can be written like this: gamma v into 1 with the v vector by c. Okay, just one comment here. Our definition, u mu is dimensionless. Okay, this is dimensionless because we're dividing by c. This is our convention. Okay, this is one thing. And easy to check, we can ask what is u mu, and you will see that's equal to +1. Okay, so this is what is happening, that we have a 4 vector, but it's a constrained 4 vector which satisfies u mu equal to 1. So it has only 3 components. So remember I told you that's a puzzle. We have a velocity which has only 3 components. We need to search for a scalar which is not there really to add to it to make a 4 vector, but this is how. So velocity is a constrained 4 vector, 4 velocity. Is this point clear? Okay. And remember, I'm not saying v and this v is constant or anything, but every instant we can associate in any frame you can get. You will have a number which goes with that. Okay. So this is something which is this point clear?
So, you repeat, how is it constrained?
Huh? How is it a Lorentz scalar? Oh, that's because it's made out of, here, d tau is a Lorentz scalar, x mu is a vector, 4 vector. That's all.
No. How is it constrained?
Because u mu equal to 1. No, nothing needed to do. You just work it out, the norm of this thing. By definition. Okay, you do the calculation, you will see. Okay, so just one more thing. This +1 again is our sign convention. So in some other books, that could be -1. Okay, this is just a warning. Okay. Okay, so we want to now define acceleration 4 vector. Any ideas? Okay, so since people are not having ideas, so let me give the idea. Again, I just do this 1 by c square. So this is the calculation. So now comes the thing, A mu now. Okay, so exercise. Show that A mu U mu is equal to 0. Okay. Actually, it's not so hard because why is it? You take d by d tau of u mu. This is equal to 0. Okay, follows from that. I won't say more. Okay, so again, acceleration is a constrained 4 vector. Okay, with the what is the constraint? It's A mu U mu equal to 0 or the 4 vector this way dot U is 0. Okay, now just I want to do a computation. How does the instantaneous rest frame so I leave it as I'll just okay, so I'll just write the answer for A mu first. I'll just write that. Should I? Okay, so no, let's do one more thing. Okay, so I need a formula. Okay, exercise. Again, remember A mu is has a particular dimension which you can extract. It's I think inverse length or something. I'll explain what this vector A is. Vector A, you can even guess. Sorry, I don't have time to come and do this calculation, but it's very straightforward. Okay, so this is the thing. And A here will be the usual thing, t square x by t square. Usual acceleration. Okay, so now in the rest frame, so the question is in the frame where u mu will be just 1 and 0, right? Where the particle is at rest. Okay, u mu will be 1 and 0. That means beta is 0. Beta vector, which is v by c, is 0. So this term will drop out. This will also drop out. And gamma u will become 1. So in this frame, A mu will be 0 and A by c. Okay. Of course, you can go back and check if A mu U mu is 0. You will see that. So what you can see here is that this 4 vector has the property that up to a factor of c, because of the dimensionality of our definition, it is nothing but the acceleration. Okay, so we can also we can do this computation of what is A mu. We can ask what is the norm of this. A 4 vector, its norm is also an invariant, and you can see that this is equal to minus A square upon c square. Now this is independent. This is a Lorentz. So everybody will agree on the magnitude of the 4 vector. Okay, up to factors of c. This is what it is. Okay, so So now I'll just define a few simple things. Momentum factor, which will agree with whatever we had written earlier. So P mu is just defined to be n, and we need a factor of c to get the dimensions, right? Okay, u mu. Okay, so just to remark, and you can check now that P mu norm will be n square c square, which we had seen before, because u mu is 1. Okay. So all we need now is to write. We need to find a 4 vector for force. Okay. So then we could write an equation which looks something like this, which looks, there are two ways of thinking about it. Write it as dp okay, or m, there are factors of c, sorry, I won't write that, so m times mu. Okay. Because my acceleration here doesn't have a diagonal, so it's mc. Yeah, it's mc times it. Okay, I hope you understand that why I'm putting factors of c, they will all go away. And so the idea here is, this is a 4 vector, so this better reduce to f equal to ma in the rest frame, instantaneous rest frame. So you remember, I'm going to this instantaneous rest frame where the particle is at rest, because it gets rid of some factor and the acceleration takes a very simple form in the instantaneous. This is a very important idea, rest frame.
So that is a 4 vector. This is a 3 component vector. How are you?
Okay. Gives. Okay. Actually, is not right. Gives. Okay, there might be more. Okay, so the additional constraint. So if you look at it, we saw that a mu u mu was 0. So the constraint on f mu is nothing but f mu u mu equal to 0. I'm just guessing. We could write. So I'm writing some. So the idea here is quite clever. We know equations in Newtonian mechanics. Number one. Second thing is, we are asking our equations to be covariant under change of inertial frames. And the third, okay, so these two things are strong enough actually to make it work. Okay, but then you start getting new things. Okay, so like for instance, what is this u mu f mu u mu equal to 0? What does it mean? Okay, so this is something which we know. So what we see here is that plane is already known. Okay, this is something called work energy theorem in mechanics. I won't work out the details. This is something which we already know. Okay, what is work energy theorem? So what does it say? Is that the work done on some particle, delta W, is some 3 vector, I'm writing now, times velocity. Work done per unit time. Okay, so F dot V, which should be delta E by delta T. Okay, so you just go back and you look at it and you figure this out. You show that this is what it is. So this is the claim. Please check this in your printer. Okay, so I'll just finish and conclude by saying that Newtonian mechanics extends nice manner to special theory of relativity. Okay, and we can, in particular, we can construct, or we can write out, we can write equations that transform nicely under Lorentz force. Okay, so I think I will stop here and okay, leave you to think about what's going on here. Okay, so so I'll stop here, and so we are done with the course. But I think there is a little bit more. I think in lecture 39 from last year, which you can read up. I put it up, and I think I have done most of lecture 38, which I wanted. But the idea is very, very simple, that we just extend things. Okay, and but then now there will be things which I haven't done, is what is the predictions of this, etc. So for instance, you could think that, can I apply a force and, keep accelerating a particle such that it can go, its speed can go past the speed of light and things like that? And the answer is, of course, no. And and people try to define some masses which are velocity dependent, which is garbage. Okay, there's only one rest mass. There's only one mass, which is called the rest mass, and which is the mass which shows up in F equal to ma. And there are no velocity dependent masses. Those are all artificial ways of trying to make some formula work. Okay, so whatever F mu, what I'm trying to say here is that the equation, if we take mu equal to I, if I equal to mai, okay, here this m is the correct equation. Okay, and the constraint is just work energy theorem. So that's not. So it's a constraint 3. So F mu is a constraint 4 vector. So it has only 3 equations which are relevant, just like we saw for acceleration and for velocity. And so that's it. Okay, so I'll stop here, and do not fall into this trap of looking for velocity dependent masses, etc. Okay, so you can ask. You will find that you cannot. What you will find is that effectively, as the velocity keeps increasing, the gamma factors which come, once velocity increases, gamma increases. So what happens is that there will be, so that we can see, you can see from, there's a gamma square or whatever term which comes, there'll be factors of gamma which will come and make it hard. You keep applying more and more and more force to get the same change in acceleration as, in velocity. And hence, so you can only reach it asymptotically. You will never ever attain that. Okay. So you need infinite energy if you wish. Okay. So I'll stop here and I'm ready for questions.